Hey everyone. In this video, I'm going to talk about one of the most fundamental theorems in probability, namely Bayes' rule. And recall from some of the previous video that there are two different interpretations of probability: the frequentist interpretation and the Bayesian interpretation of probability, right? Um, and the Bayesian interpretation of probability implies that it measures one's subjective belief of an event's occurrence rather than the relative frequency under repeated experiments. Okay, so from this perspective, it is natural to ask the question of how we should update our beliefs after observing some data. So after observing some data, how should we change our belief about the probability of an event occurring? And Bayes' rule ultimately shows how updating beliefs can be done in a mathematically coherent manner. Right? So it's fundamentally related to this Bayesian interpretation of probability, quite obviously, given the name. But it's important to keep in mind that Bayes' rule and the relationship and the formulas that I'm going to show you in a second hold regardless whether you kind of adhere to the Bayesian interpretation of probability as a subjective belief or to this frequentist interpretation of probability. Okay, the mathematical relationship of conditional probabilities still holds. Okay, so let's jump right into Bayes' rule. Remember from the conditional probability formula that we talked about in the previous videos, we can express the conditional probability of event A occurring given that event B occurred as the fraction between the joint probability and the marginal probability. So the joint probability is the probability of A and B occurring, so A intersect B, and the marginal probability is just the probability of B occurring irrespective of A, right? And essentially what Bayes' rule or Bayes' theorem implies is we're basically using two rules that we saw before to express the joint probability and the marginal probability in different ways. Specifically, using the multiplication rule that I showed you, as well as the law of total probability, we can kind of express this fraction as follows. For the numerator, the joint probability, we just use the multiplication rule and express the probability of A intersect B as the probability of B conditional on A times the probability of A. For the denominator, probability of B, the marginal probability, remember that the law of total probability allows us to basically express the probability of, or the marginal probability of B occurring, express how this total probability of an outcome can be realized through distinct events, right? On the one hand, we have the A occurring and the probability of A occurring, and have the probability of B conditional on A occurring, as well as A not occurring, so A complement, times the probability of B occurring conditional on A not occurring, right? So in the sum of those two probabilities through those two different events combined are equal to the marginal probability, okay? So combined, by combining basically the multiplication rule and the law of total probability to express the joint probability and the marginal probability respectively, we basically have a clear expression of the conditional probability of A given B that is now re-expressed as a combination of the kind of inverse of probability of B given A, the probability of A, as well as the probability of B kind of re-expressed as this using the law of total probability, right? So in other words, knowing the probability of A, the probability of B given A, as well as the probability of B given A complement, so not A, is enough to compute the probability of A given B. All right. So we're basically now able, based on the marginal probability of A, as well as the complement conditional probabilities, we're able to compute any conditional probability A given B. Right. And that's the essence of Bayes' rule. Okay. And again, it's important to note that this relationship between conditional probabilities holds whether we interpret probability as a subjective belief or in the frequentist manner, right? Bayes' rule basically shows us mathematically how the knowledge of the probability of A occurring, the marginal probability of A occurring, which sometimes is also called the prior belief or the prior probability, combined with the probability of B conditional on A and the probability of B conditional on not A or A complement, which you could think of as kind of the likelihood, yields the probability of A conditional on B, which we could also describe as the posterior probability, right? So Bayesian updating is ultimately describes this process of having a prior belief, which in our case here would be the probability of A occurring, and then we observe some data, which we kind of can think of as observing B, and those two elements together allow us to compute the probability or the posterior belief, which is the probability of A conditional on or given that B occurring. Okay, so let's look at a quick example and one kind of canonical and fun example is the Monty Hall example that kind of exemplifies Bayes' rule, right? The Monty Hall problem works as follows. It's basically a game show where a contestant chooses one of three doors. Hidden between two of the three doors is a donkey, and the third holds a prize. Okay, so Monty Hall opens one of the doors after the contestant has chosen one of them, and Monty Hall opens another one that was not chosen and reveals a donkey. And then proceeds to ask the contestant if she wants to switch doors after one has been revealed. Um, and so now the question is, does the contestant benefit from switching the door after this revelation, or to stick with the door that was initially chosen, right? So to what extent are the chances of success improved by switching rather than not switching, right? And so the interesting thing is, the first prior intuition would be that all doors have the same probability of holding the prize 1/3, so it shouldn't really matter whether you switch or not. The probability should still be the same. But it turns out it is not. Okay, and why that's not the case? We're going to go through that now real quick. I should also note I included a link. There are other videos out there as well, but there's a link that kind of goes through that problem and an explanation as well. So feel free to check that out as well if you kind of want to hear a little bit more or someone else talk about that, right? So the problem is, suppose we picked door A. There are three doors, A, B, and C, and Monty opens door C that has a goat, right? Should we now switch to door, it says door C, but it should of course be door B. Should we switch to door B after door C has been revealed to be a goat, okay, or have a goat behind it, okay? So our prior belief, of course, is that the probability of each door has to hold the prize is 1/3. So the probability of A is equal to the probability of B to the probability of C, which is equal to 1/3, right? The data that we observe is that Monty reveals C, okay? So C is revealed and it doesn't hold the prize, right? Now the question is, what about our posterior belief of the probability of A holding the prize conditional on Monty revealing C, and the probability of B holding the prize conditional on Monty revealing C, right? And the question, of course, is, are they the same? Or is the probability of A conditional on Monty revealing C smaller than the probability of B conditional on Monty revealing C, right? In that case, we would want to switch because that would maximize our chances of winning the prize, okay? So now let's apply Bayes' rule to that problem. The probability of A conditional on Monty revealing C is, just applying this formula, equal to the probability of Monty revealing C conditional on A times the probability of A divided by, and now we separate the marginal probability of Monty revealing C into three separate elements, right? So rather than A and A complement, we separated in all three different possibilities. The first possibility, probability of A holding the price times the probability of Monty revealing C conditional on A holding the price. Then we have the probability of B times the probability of Monty revealing C conditional on B holding the price, and probability of C holding the price times the probability of Monty revealing C conditional on C holding that price. Okay, so there are a couple of things to note here. One, of course, is that the probability of Monty revealing C conditional on A conditional on A actually holding the price is 1/2, right? So if the price, if you actually chose, if the price is behind door A, then Monty has basically a 50-50 chance to choose either C or B, the door, because Monty, of course, wouldn't reveal the price, so it would be a 50-50 chance which door would be revealed. If if the price is behind door B, then the probability of Monty revealing C is equal to 1. Why is that the case? The contestant, or we, chose the first door, so the first door won't be revealed. If the true price is behind door B will not be revealed, so the probability of Monty revealing door C is equal to 1. That's the only door left. And then lastly, the probability of Monty revealing C conditional on C actually holding the price is of course 0, because the door that holds the price will not be opened. Okay, so if we plug those in, including our prior values for A, B, and C, which are all 1/3, we have the probability of A conditional on Monty opening door C is 1/2 divided by 1/2 plus 1 plus 0, which is equal to 1/3. So keeping with door A implies that our winning probability is just 1/3. Similarly, if we do the same thing for the probability of B conditional on Monty revealing C, we again can plug in Bayes' rule here and plug in those values. It turns out that the probability of winning after switching to door B is actually 2/3, right? So in that case, it is better. You basically maximize your chances of winning in this game by switching after one of the doors has been revealed, right? Another kind of related problem involves is the prisoner's paradox, which involves three prisoners. Two of those prisoners are about to be released, but only the warden knows which of the two. Okay, and now one prisoner asks the warden to secretly tell him the name of one of the other two prisoners who is to be released. And he argues that since he knows that at least one of the others is to be released, it won't change anything if he is given this information. But once the warden complies, the prisoner regrets his request, for he now thinks that his chances of being released have dropped from 2/3 to 1/2. Right. So when asked so ultimately the question is this reasoning correct? Right. So at first there's a 1/3 probability, or there's a 2/3 probability of being released. And one prisoner then asks the warden, who of the other two are you going to release? And then says afterwards, okay, now that I know that one of them will be released, my probability kind of shrank from 2/3 to 1/2. So the question is this accurate? Sorry. Here's another description. Oops. Oh my. Another description of this problem. Three prisoners, A, B, and C, are on death row. The governor decides to pardon one of the three and chooses at random the prisoner to pardon. This is actually a reverse case. He informs the warden of his choice, but requests that the name be kept secret for a few days. The next day, A tries to get the warden to tell him who had been pardoned. The warden refuses. A then asks which of B or C will be executed. The warden, so I switched up the explanation a little bit. The warden thinks for a while, then tells A that B is to be executed. So the question now is, did the warden give A any information about whether A will be pardoned, right? It's the same kind of underlying logic, but it's just one person being pardoned rather than two, okay? So again, we start with the probability of pardoning is equal across all three prisoners, 1/3. And now W is the event that the warden says B is to be executed, right? And now the question is, what is the probability of A conditional on this event, that observing that the warden says that B is to be executed? And again, we can express this as the fraction of the joint probability divided by the marginal probability, and of course the probability of A intersect W is equal to the probability of W conditional on A times the probability of A. And those probabilities are 1/2 for that's the same logic. The probability of the warden mentioning B conditional on A being pardoned is 1/2 times 1/3. That's 1/6. The probability of W is the probability of again using the law of total probability. It's the probability of W intersect A plus the probability of W intersect W intersect A plus the probability of W intersect B plus the probability of W intersect C, which we can again write using the multiplication rule as these conditional probabilities, and again we know the probability of W conditional on A is 1/2, the probability of A is 1/3. The probability of W conditional on B being pardoned is of course 0, because then he wouldn't mention B. The probability of B is 1/3. Then the probability of W conditional on C is again is 1, of course, because you wouldn't tell the prisoner A that he is being pardoned. And probability of C is 1/3. So here the probability is 1/2, right? So that means the required probability is still 1/6 divided by 1/2, so that is still 1/3. So essentially that means the probability of being pardoned is still 1/3, conditional on the warden having told prisoner A that prisoner B will be executed. All right, so those are two examples. Kind of go through them. I'm gonna try to go through the logic. Maybe try to kind of compute those conditional probabilities on your own as well, and we can talk about them a little bit more in the Q&A session as well. And in the next video, we're going to talk about random variables and probability distributions, and I'm going to fix that typo.